You know, life is about choices. Should I have this dessert or that one? Should I study now or later? And often, these choices are not based on one factor, but many. In the world of mathematics, this is where we start caring about finding the optimal ways to combine a number of factors in order to attain the best possible outcomes, always depending on the context. This concept is known as multivariate optimization. Multivariate functions consist of two or more variables. For instance, a company's profit might depend on the quantity of labor and capital used in production. Multivariate optimization helps find which combination gives the highest profit, or in technical terms, the maximum of the function. Consider this particular function of x and y, with these two variables representing the quantities of labor and capital, respectively, used to calculate the profit from the hourly production of pizzas. The first step for optimizing multivariate functions is to find the two first-order partial derivatives. We can do this by interpreting y as a constant when we differentiate with respect to x, and interpreting x as a constant when we differentiate with respect to y. If this sounds a bit weird to you, I recommend checking out my previous video exclusively on partial differentiation. I go through a few examples and fully worked out solutions. Make sure to watch it. Once we have these two first-order partial derivatives, we set both of them equal to 0 to find the optimal combination of x and y. In this example, the optimal x is 7, and so is the optimal y. And if we plug these values on the original function, we find that the optimized profit is equal to 90. However, there is a plot twist. Knowing the optimal point is half the story. We also need to know whether this point is a maximum, a minimum, or a saddle point. This is where the Hessian matrix comes into play. For two variable functions, the Hessian matrix is comprised diagonally downwards of the second-order partial derivatives and comprised diagonally upwards of the cross-partial derivatives. In particular, we look at the determinant of the Hessian matrix. For two variable functions, the determinant is found by multiplying the two second-order partial derivatives and subtracting the square of the cross-partial derivative. If the second-order partial derivative with respect to x is negative and the determinant is positive, the critical point we previously found must be a maximum point. If the second-order partial derivative with respect to x is positive and the determinant is also positive, the critical point we previously found must be a minimum point. Or, if the determinant is negative, the critical point we previously found must be a saddle point. This point in particular can be a bit tricky to understand. In a nutshell, it looks like a Pringle, but more accurately, think of a saddle point like a mountain pass. It is higher than the surrounding valleys, but lower than the peaks around it. It is neither a complete high nor a total low. For more accurate visualization, we can now use Wolfram Mathematica to get these solutions instantly and check if our work is correct. I made this quite lengthy code which plots any function similar to the one we defined previously for the profit from pizzas. This lets us see the different forms that similar functions can make: peaks for maximum points, valleys for minimum points, and a particular mixture of both for saddle points. By using these sliders, you can play around with different coefficients and observe how they affect the 3D shape of the function and its optimal point, whether it becomes a maximum, minimum, or saddle point. You can find this tool on my website using the link in the description below. You know, the world of economics, especially in the field of production and costs, loves multivariate optimization, but it's not just them. Physicists, biologists, and even game developers use it to solve their complex problems. As you continue your journey with multivariate functions, always remember that each function tells a story, and optimization lets you understand its inner workings.